All right, everyone, continuing the application track of Spark Summit Europe 2015, please welcome a researcher from IBM Research, Paula Tashma.
Hello, I'm going to be talking about how Spark, Okay, right. I'm going to be talking about how Spark enables the Internet of Things, efficient integration of multiple Spark components for smart city use cases. And this is a work that's funded by the Cosmos, by the European Union as part of the Cosmos Research Project. And we're doing this together with our partners, Atos, University of Surrey, and this is done for Madrid Council and MT Madrid Bus Company. So people here generally know about Spark, but I want to ask how many people here feel familiar with Internet of Things? Raise your hand. Okay. So just to talk a little about Internet of Things and why I think it's very important is, well, way back people had much kind of slower ways of collecting the data. These days, Internet of Things, we're talking about devices which have chips, sensors inside them which can connect to the internet, communicate their data autonomously, and then some of them actually can also support actuation. So we can also control these sensors. For example, turn off lights, lock a door in a home, and so on. So what this means is that data can now be collected much in a more massive scale, much faster. So we have a lot more data, actually. Now, sensors is not something new. People have sent rocket ships to space. Obviously, sensors are involved, but what's new here is the economics has changed. Sensors are getting way cheaper, and this enables Internet of Things to be commoditized so that we can put sensors at a large scale in agricultural fields, collecting data. Sensors can belong to many, many places, and this is what the Internet of Things is about, the commoditization of sensors and collecting data and acting on data in that way. So I want to claim now that the Internet of Things is the biggest kind of big data. And by 2020, the number of network devices is said by IDC to be 30 billion, more than 4 times the global population. So this means that the Internet of Things is going to generate a lot more data than what we might call the Internet of Humans, is what the Internet has been up until now. So what we are seeing is that this data is very large because not only are we recording, say, sensor readings, for example, temperatures, blood pressures of patients, and so on, but sensors can also send images, they can send video, they can send sound. So we're actually getting all the kinds of data we had, for example, with social media, and even more. So now I'm going to focus more on actually what we did in this space. So we are working with the MT Madrid Bus Company, and they need to make decisions in real time according to the current state of traffic and future state. The problem is that we see, I've been to a control room in Madrid where there's many people stationed there looking at screens needing to manually respond to any traffic incidents that come up. So our objective is to improve customer satisfaction by allowing a response in real time more efficiently and faster. So the approach is to monitor data from up to 3,000 sensors located in different positions in the city of Madrid. This is open data. Anybody can access the data. We are continuously collecting the data and storing it on our platform. And Madrid Council and the EMT Madrid Bus Company can respond to the insights we gain by performing all kinds of actions. For example, they can see a traffic problem. They can automatically reroute a certain bus line. The Madrid Council could change traffic light patterns in a certain location. Passengers could be alerted, and so on. So the point, one of the, our contributions here is that we are basing what we do in real time on what we've learned from historical data. So I think this is an important contribution. So what I'm going to do now is I'm going to go through our system kind of in a bottom-up flow. This is going to form three sides of a triangle. So first I'm going to talk about the bottom side. So this is, here we see the bottom side of the triangle is starting off on the left-hand side with the devices. Those devices are generating data. Either we need to manually pull the data out and push it into Kafka ourselves, or in some cases, those services could subscribe to our platform and send the data themselves to Kafka. Kafka, I've seen it mentioned in other talks here. It's a message bus type service where there are topics, and you can publish data to those topics and subscribe to those topics, similar to RabbitMQ and so on. So second in the chain is an open source tool developed by Pinterest called Secor. What Secor does is it works together with Kafka. It takes multiple messages from a Kafka topic, aggregates them together, and stores them in object storage. So up until now, it supported only Amazon S3 as its object storage. We added OpenStack Swift as well. We added support for that. In addition to that, I'll mention that we are storing the data. We want the data to be structured. This is IoT data. So the data we're talking about is from traffic sensors in Madrid. Each data reading will be a JSON, say, record. It will have a timestamp. It'll have traffic speed, traffic intensity. It'll have some kind of ID saying what sensor this is coming from, and other data. So this is kind of semi-structured data. We want to store it in Parquet format so that we can access it using Spark SQL. In addition, we want to index the data so that we can access it efficiently. I'm going to talk about that in a bit more detail later on. Okay, so we finished the bottom side of our triangle. Now we're going to kind of look at the right-hand side going up. So what we talked about before was ingestion. Now we're talking about data access and what we actually do with the data, so analytics. So first of all, we use Spark SQL to access the data. And as I mentioned already, we indexed it so we can access it using Spark SQL more efficiently. Secondly, we're using Spark machine learning library algorithms in order to gain insights from the data. And in practice, what we're doing is we're thinking that traffic in general can be kind of simplistically split into two cases, good traffic and bad traffic. And what we want is to be alerted when traffic goes from a good state to a bad state. At that point, we might want to do something like reroute buses, change traffic lights, alert users, so on. So that's what machine learning is doing. It's using clustering to do that. And it's generating thresholds for when you're moving from good to bad traffic, which are then going to be input into the next real-time side of the triangle. Okay, so the final side of the triangle is what's kind of happening in real time. We are using complex event processing for that. And it's a rule-based system. It takes the thresholds from the machine learning and applies them. So you can notice here that it's actually getting data in real time from Kafka. It's applying the thresholds and in real time able to respond to whatever conditions come up. So just want to point out that the green arrows here are the real-time flows. That's all happening in real time. But we wouldn't be able to make intelligent decisions in real time if we hadn't done all the background work, all the batch processing that's needed in order to generate the thresholds intelligently. And I'm going to talk a little bit more in depth about that as well. Okay, so what I'm going to do now is each side of the triangle, I'm just going to kind of go zoom in and go one level deeper. And then I'm going to show a recorded demo of what we've done. So back to the ingestion flow. What we're doing is we're continually collecting data from a subset of the 3,000 Madrid Council traffic sensors that exist in static locations. This data is published, it's open data. We're accessing it via a web service and pushing it ourselves into Kafka. And as I mentioned before, traffic speeds, traffic intensities, it's updated every 5 minutes. And we're using Secor. Secor works according to policy. We can say we want to create a new object every time we hit, say, 1 megabyte. Or alternatively, it could be a time-based policy, so we could create a new object every time 60 minutes passed. And we, in our case, have partitioned the data according to date. So, for example, if we take a look here, this is what our Swift objects look like. It's actually a flat namespace, but the object names have slashes inside them, and this is basically what partitioned data looks like, systems like Hive, and it's supported by Spark SQL. So by this way, you can actually access objects from a particular date by requesting only those, and you don't have to touch the other objects. The thing about partitioning is it's kind of, you have to set it up, it's a hierarchy, you have to set up the hierarchy statically, you can't kind of change it as you go along. We are using Parquet format that's nice for IoT data. You can do column-based compression, which is great for IoT data. And you also only need to access the columns that you want. You don't even have to read from disk columns that are not required. We extended Secor by allowing it by supporting converting the data into Parquet format. And we also extended Secor by allowing annotation of metadata with objects. So Swift, when you create an object, you can also annotate it with metadata. And the kind of metadata that is useful in our case is we are recording the minimum and maximum values of certain columns, so to speak. So the columns we're interested in here are timestamp, traffic speed, and traffic intensity. So this is what the metadata looks like for the objects we've stored. For example, here you see the maximum timestamp for a certain object in OpenStack Swift. So how this turns out to be important is that machine learning does the learning according to sensor, so we're creating a model per sensor, but also for each time period separately. Because as we all know, traffic is different in the morning than in the afternoon or evening. Rush hour is different from nighttime, weekends different from weekdays. So we do learning according to the context. So when we're accessing the data in Swift, we want, say, all the data for just morning periods. So we generate a query that looks like this, where we have a selection based on the timestamp. And since we've indexed the objects according to timestamp, we only have to get access on disk and send across the network those objects which overlap the time period that we're looking for. So this gives us, in an example run that we did, it significantly reduces the number of requests to OpenStack Swift that we actually have to run by. In our case, it was more than 20 times improvement. Okay, so now I'm switching to machine learning, talking about that in a little more detail. So as I said already, depends on context. We are using Kmeans clustering, where k equals 2. That's the number of clusters we want. We want good versus bad traffic. I should point out that the Spark MLlib has a number of algorithms. You know, we chose one of them for this problem. For another IoT problem, another algorithm could be chosen. What we're doing is we're taking the center point of each cluster. We have 2 clusters. Then we take the midpoint between the 2 clusters' center points, and that's going to serve as the basis for the threshold, which divides between good and bad traffic. Another contribution here, which is nice, is how, I mean, as new data comes in, we've done the machine learning for a particular sensor, for a particular, say, morning interval. At some point, new data is going to come in and things change. So how often do we need to rerun the algorithm from scratch and generate a new model? So there is a technique called silhouette index, which is a generic technique. We can use it here. We can use it in other use cases as well, which can measure the index quality. It ranges between -1 and 1. And when it drops below 0.5, then we rerun the K-means clustering again and generate new thresholds. So this is what morning traffic on weekdays looks like. The blue dots are is the good traffic cluster. The red dot is the bad traffic cluster. We have the 2 centers and the midpoint between them, which is used to generate the threshold. So just another point is that we could use similar techniques to do anomaly detection as well, which is also of interest for IoT use cases. We could take just a single cluster, and as soon as the data point is is far enough away from the center in a statistically significant way, then we say this is an anomaly and classify it as such. Now I'm going to talk a little bit more about the final side of the triangle, which is what happens in real time. We use complex event processing, which is a rule-based approach. It processes events record by record. CP rules are typically defined manually, but in many cases it's difficult to get them right, actually. So what we're doing is we're automating this process on the one hand, and we're also making it smart so that automatically generating the thresholds. And it turns out that this is actually can be tricky for humans to do this correctly. We are using a component called microCP, which has a very small footprint and can be run at the edge close to the device. So this is nice for IoT use cases, and we're running this on a Raspberry Pi. So that makes it a little different from something like Spark streaming, which really should be run at the back end. So work in progress is that we're also looking at using Spark streaming linear regression to predict traffic, say predict what's going to be like in the next 5-10 minutes. And then we can apply CP not on the real-time data, but on the predicted data. And then we can kind of give a heads up, proactively respond to what we think is going to happen in 10 minutes, and perhaps take action earlier and avoid problems that way. So now I'm going to switch to a recorded demo of what we've done. So back. Okay, so just before I even start, actually, I just want to just tell you how this is kind of set up. What you see here is 3 sensors in Madrid which are being tracked. Actually, there's more, but we're just showing 3 for the purposes of this demo. And underneath the map, we see actually 2 out of the 3 sensors. The third one we'll see once we scroll down. We see the speed and intensity values for these sensors. And in a minute, I'll start the recording, and we'll see how things progress. But this is, as you can see, as you will see, it's going to be updated new traffic speeds and intensities. Now, on the right-hand side, there's a window at the top right for MQTT topic, which is collecting thresholds. So as soon as machine learning publishes a threshold, it's going to go to the top right box. And the bottom right box is the window where we're going to be running machine learning script. So as you can see here, first of all, we're starting off the Python shell for Spark, and we're including a jar file which includes our Spark SQL driver, which uses metadata search as I talked about previously in more detail. So now you see the Spark shell starting up, and now we're going to run a Python script which is doing the machine learning. Try and get rid of this. That's better. So here we see the metadata search, which is generated by the machine learning query that's run. This is actually running machine learning for the first sensor, and once it's done, once it's generated thresholds for that, it will move on to the second and third sensors, and even, I think we've got running here 12 sensors or so, so after the 3, it'll keep going to the 4th and so on. So what we just saw now was the thresholds were just generated for the first sensor. So we have threshold speed of 42 and intensity of 678. This is what it looks like on the MQTT topic. And so far, so good. Everything, the speeds and intensities are above the threshold, so everything's fine. The machine learning is continuing to run now on the second sensor. It's generated the thresholds now. We have 41,513. Machine learning is continuing to run now on the third sensor, which is seen at the bottom of the screen now. And now we see 33,616. Everything so far is normal. All the speeds, intensities are above the threshold values. And okay, so now we have actually what happened now, no thresholds changed for this sensor, but we got some new data from the sensor in Madrid. The intensity actually went down and is now below the threshold. So we are flagged this as abnormal. And now Madrid bus company can go and take whatever action it wants to take. Now, what I'm showing now is behind the scenes. This is what the data looks like in OpenStack Swift. We see data in Parquet format, and each one is compressed. So I'm just chose a particular object, and I'm going to use Swift's REST API to take a get of that object and look at the data. It's binary format, so it doesn't seem to make much sense, but at the end of the object, we actually see the schema. That's how Parquet works, has the schema inside the object. Now, by taking a head of the object, that's the REST call to see the headers, the metadata, and we can see here minimum, maximum timestamps, for example, that we've stored with the data. So what we're going to see now is the kind of the other window, which is looking at the Python script, which is running the machine learning. So here we see if things are, depending on the time of day, we run a different, we look at different data sets. We have 12 sensors here. Now we see our Spark SQL driver being called, and the SQL query is running between, I think I missed exactly the times there. But what we can see now is Kmeans clustering being applied in a pretty straightforward fashion. We're using it, we're getting 2 center points, we're taking the median point between those. And then finally, we publish the thresholds to an MQTT topic. I think this demonstrates that we're using Spark SQL, machine learning in a modular way, pretty much out of the box. In some places, we have made extensions. For example, the Spark SQL driver we wrote. We extended Sakor and other things, but other places we kind of combine things together in a modular way. So 2 more slides. I think one point here is that our architecture applies to many IoT use cases. It's not just for Madrid traffic. It could be used for anomaly detection, for pipe leakage, for appliance malfunction. We're actually also working on another use case in the Cosmos project, which looks at that for smart homes. And many other use cases. There's healthcare, insurance, transportation, logistics, and so on. And finally, I want to end this talk with recently, just the last month or two, this work was jointly by us and Naim Altaf and his team in IBM, was ported to run on IBM's platform as a service offering called IBM Bluemix. And Bluemix has services for most of the components that I mentioned today, including Apache Spark, including object storage or open, like Swift, basically. It also has a message hub service, which is based on Kafka, and also Node-RED, which I didn't mention, but actually we did use it. And this is now running on Bluemix and was demoed yesterday as part of the IBM Insight conference. And the point of this was to show to customers that what kinds of things, what kind of IoT examples can be run on the Bluemix platform. So I'd like to thank everybody. Maybe I'll switch quickly back to the very first slide so you can just see my email address if people want to contact me. And I'm going to be here the rest of the day and tomorrow, and we'll be glad to talk with anybody who wants to talk about this.
Thank you, Paula.
So, no time for questions?
Sorry, that's fine. Yeah, that's fine. We have 5 minutes till the next talk.
Oh, okay.
Sorry.
Okay.
I didn't realize that was that. Okay, next talk will start in 5 minutes.